All right, so the end of the first 4.1 video that I did was also terrible. I apologize. I kind of lost my mind for a second. I'm sure you guys are used to that happening in the classroom, but at least there I can kind of fix things without ruining the whole video. So there's a couple things that I want to make sure that I either state differently or kind of reemphasize here. And the first is that I mentioned as we set this up that we're almost always working with closed intervals where we're including the endpoints, because otherwise the absolute maximum and minimum don't necessarily exist. Another thing to make sure that you're aware of is that we do need to be working with continuous functions. Right? If we have an asymptote right in the middle of our interval, there's no way we're going to be guaranteed to have a maximum or a minimum value. And so let's just take a quick look at that and do an example where maybe you're looking for the absolute min and max of the function. Just to make it nice and straightforward, function 1 over x over -1 to 2. Okay, so excuse me. So in this situation, we don't have a problem with the endpoints. We're including the endpoints. That's good for us. But 1 over x, and you can see immediately that is not continuous over that whole interval. There's going to be an asymptote, because of what we know about the graph of 1 over x, there's an asymptote at 0. And so this is one of those circumstances where if you come across something that's not continuous, you're going to have to do this a little bit differently. You can't just automatically say, okay, let's find the critical values and find the endpoints and evaluate. Because it's just not going to work. Well, we'll see that in a second. So just a reminder, if you go to graph f of x is equal to 1 over x, the asymptote again is right on the y-axis. And this is not the perfect graph, but 1 over x looks something like this. Okay. So if we're looking at the maximum and minimum value between -1 and 2, we're looking at, say, -1 is right there and 2 is over here somewhere. Basically, we're just trying to cut this out so that we're going from, I guess, -2 on the right-hand side and -1 on the left-hand side. Okay, and so just taking a quick look at it, it's hopefully absolutely clear that, the endpoints are not maximum or minimum values, right? This is not a maximum because the graph's certainly going up forever. This is not a minimum because the graph is going down forever. There's just not going to be any absolute extrema on this graph due to the asymptote. So I will say, depending on the discontinuity, every once in a while you can draw a graph and make sense out of something of what's going on. But in general, that's why, if you look at the textbook, every single one of the theorems and most of the problems and the practice problems are all saying, hey, assume that the function f is continuous, or here's a continuous function, find its absolute extrema. So just be very aware of that. So, obviously, some functions are trickier than others, like 1 over x is obviously going to have an asymptote. But there's other functions that we've seen that have asymptotes in different places for different reasons. So just be aware of that. Okay, so let's just change this up just a tad, just to make sure that you're aware that it's just not automatically going to not have any extrema if you have a discontinuity. It just might not have both of them. And so if I just change this to a 1 over x squared, we have almost the same setup where we still have an asymptote right on the y-axis. For the graph of 1 over x squared, because we're squaring, it's always positive. So instead of having half of it above and half of it below, we have this sort of thing going on. And so this time, if we're guessing about where the values are, we're looking between -1 and 2 this way. Well, you can definitely see that there is no absolute maximum because it's going up forever, but there definitely should be an absolute minimum. There is a point somewhere in here that's lower than the rest. Okay, I don't have any idea whether I graphed this perfectly or not. I don't think that I did. And visually, it looks like that should be the minimum, but I'm pretty sure it'll end up being over here. So, this is a circumstance where you might as well go ahead and go through the process and see if we can find any critical values to pair up along with our endpoints. But you should be able to visually see that one of our endpoints should be where um, the minimum value is. So let's just go ahead and work through this. So first of all, you can use the quotient rule here. I don't know that we ever had a chance to talk through this in a previous video. You can use the quotient rule here, but it's just as easy to rewrite that using a negative exponent. 1 over x squared is the same thing as x to the negative second power. That way, when you go and take the derivative, you can just use your normal power rule, multiply by the exponent, and decrease it by 1. And again, so it's a little bit more easy to see how we're dealing with this visually, write the negative exponent back as a fraction. And you can see here that if this is going to be set equal to 0, it just won't work, right? The numerator is never 0. That's the only way that this would ever be equal to 0. So the derivative equals 0 has no solution. And we can see that the derivative does not exist when we're dividing by that 0. The derivative does not exist at x is equal to 0. Okay, so I just started going with this, and I did not realize that you guys couldn't see that one. But make sure that you remember that a critical value needs to have one of these two be true, but it also needs to be on the interior of the domain. X equals 0, that's not even in the domain. So that can't be a critical value because x equals 0 is not something you can put into the original function. Okay, so what that tells us then is that in this instance, there are no critical values. And so we know that we're just going to be evaluating it, the endpoints. And again, the only reason that we're allowed to do this is because we know what this graph looks like. If we didn't know what the graph looked like, we would just have to say, hey, not continuous. We have no idea what's going on. Maybe it has a maximum, maybe it has a minimum, maybe there's a gap in there. But knowing what we know about this graph, we can just come back and check that. If we evaluate the function at -1, we're going to get 1 over -1 squared is +1. So 1 over 1 is 1. If I put in 2, excuse me, 1 over 2 squared would be 1 over 4. And that's certainly smaller than the other value. Keep in mind, we're only looking for the minimum because there's certainly no maximum. So this would have no absolute maximum, but we do have an absolute minimum. Oops. Let me rephrase that. We have an absolute minimum of, the minimum value is 1/4 that occurs at x equals 2. Okay, so that's a problem that's not really in the textbook because it's not something that you can technically do all the way with calculus and critical values. But that's why, again, the textbook talks all about working with continuous functions. And even though I haven't given you anything with open intervals where the endpoints are not included, that's also why it always includes the endpoints. Because if these endpoints weren't included, we wouldn't be able to do anything here. And so again, there's actual rules and formulas from the textbook if you want to look at it in a technical sort of context. But when you're finding the absolute minimums, maximums of a function, in general, we want to be talking about a closed interval, and it's almost crucial that we're working with a continuous function. Otherwise, there's a lot more going on that you have to take care of. And so that was one thing that I wanted to kind of reestablish. The other is just the last sort of idea that I talked about in the previous video. We didn't actually do an example because, like I said, and all my mumbling at the end, I just had forgotten about that theorem until I was actually doing work on the board and decided I should say something about it. But since I hadn't prepared anything, it did not go terribly well. I'm going to move this back a little bit. And so just to restate that, if there's exactly one local extrema. So remember, with the local extrema, that's where the derivative is either equal to 0 or it does not exist. But there's exactly one local extrema in the entire domain, then it is also an absolute extrema. And I like to say absolute max or min here just so I can restate, again, same thing that we said earlier. there can only be one local extrema. That doesn't say there's one local maximum and one local minimum, just total one local extrema. Then that extrema is either the absolute maximum or it's the absolute minimum. And it just depends on the problem. And so that's what I want to make sure that we see an example of here. So this time, I am going to be a little bit more obnoxious and give you something where we have a little less information, where it just says, hey, let's find the absolute extrema. You know what, maybe I should be a little bit more specific. I'll go ahead and give a little bit of this away. Let's go ahead and say we're finding the absolute maximum of the function g of x is equal to x times e to the negative x. Okay, so I'm giving away a little bit of the problem at the beginning just so it's a little bit easier to comprehend as we go through this. But in subsequent sections where you're going to talk a lot more about how you can tell whether it's going to be a maximum or a minimum without being told. So some of the problems later on will just tell you to find the extrema. Okay, so here, if it just asks you for an absolute maximum but doesn't give you an interval, we have to be assuming that we're talking about the absolute maximum over the entire domain. Okay, so we have to figure out what the domain of this function is. There's two separate pieces of the function. The domain of x is anything, right? We can put anything in for x. And think about e to the x, or e to the negative x. It doesn't matter what number we put in here. We can evaluate that exponent. Even if it's a 0, e to the 0th is 1. Doesn't matter if you're evaluating a negative exponent, positive exponent. So here, just to be clear, the domain is all real numbers. And that is certainly way different than what we've been doing so far, because there's no way to plug in negative infinity, infinity as endpoints to determine what a maximum minimum value of this function is. Okay, so now that we have that written out, we should be aware that most likely, at least, we're going to get a maximum or minimum from a local extrema. I guess going back to how we started this, you knew that ahead of time because I was telling you the theorem that we are going to end up using here. So let's go ahead and find our derivatives so we can find our critical points, critical values. Okay, so here, that is multiplication, so we have to use the product rule. So it's the derivative of the first function times the second plus the derivative of the second function. So be careful here, there's a negative in the exponent here, so it's actually going to end up being technically the chain rule. The derivative of e is itself, but excuse me, we also have to take the derivative of its exponent. The derivative of negative x is negative 1, or just negative e to the x. And we still have to multiply times x. So maybe I should put parentheses around that. Okay, so again, derivative of x times e to the negative x, derivative of e to the negative x times x, and just writing it more nicely. Not quite like that. 1 times e to the negative x, of course, is e to the negative x. Adding and subtracting, sorry, adding a negative is like subtracting, and we just switch the order here so it looks a little bit more nice. So that is our derivative. Okay. So now we need to set that equal to 0 and see where this might be undefined. Let's actually start with undefined because there's nothing to write there. Just like we talked about, we could plug anything we want in here. Same thing's going on. And this is just an exact copy of what we started with. E to the negative x, we could plug anything into. So this is always going to exist. So all we care about is when is this guy equal to 0. And so to solve this, a little bit different than some of the ones you've seen before, but there's definitely an e to the negative x that are in common here. So we can pull that out as our common factor. E to the negative x divided by itself will leave you with a 1. Over here on the cancer, and leave you with an x. And then technically, you split this up and you get e to the negative x is equal to 0, or 1 minus x is equal to 0. And we've said this a million times before spring break, but e raised to any exponent is never going to be 0, so you can just forget about that. And this solves super quickly. And you get x equal to 1. Okay. So this is where that theorem that we had before comes into play. And there's one critical value, which means there's going to be one local maximum or local minimum, which means it's automatically going to be the absolute maximum or the absolute minimum. Okay, so what we know, because I told you, what we know right now is that f evaluated at 1 is going to be the absolute maximum of the function f of x. And so we're going to double check and make sure it's a maximum here in just a moment. But first, we have to evaluate. It's not f, is it? Sorry, that was g that I started with. We have to evaluate g at 1. So we're looking at 1 times e to the negative first power, which is 1 over e. Okay. And I forgot to write down what that exact value is, but e is about 2.7. So we're looking at something like maybe 0.35, somewhere in there. Okay. So I won't even try to guess and write it on the video and have proof that I'm an idiot and don't know how to divide 1 divided by e, but that is the value that we're looking for. Okay. And again, g of 1 is the absolute maximum, so 1 over e is the absolute maximum, and it occurs at x equals 1. Okay, so that's really what we're looking at for an answer here. But let's just verify that that's the absolute maximum and not the minimum. But we don't actually know whether this was a local max or min. We just knew that there was something there, so it had to be the absolute something. And we just kind of cheated, where I just stated, hey, that's going to be the maximum. So all we have to do to check whether this is the absolute maximum or absolute minimum is just put something back into the original function. It doesn't matter what you put in, as long as it's not this x equals 1. If I put anything else in for x, it better be smaller than whatever 1 over e is. Okay. And likewise, if this was going to be an absolute minimum, which it's not, but if it were, we'd have to put in any number we wanted and show that that number was bigger than the minimum we came up with. Okay, so I again thought I had enough room. Right, so just a quick check here. The easiest number to plug in is 0. So check that. G of 0 would be 0 times e to the 0th, which is, of course, just 0. 1 divided by e is a small little decimal, but it's certainly larger than 0. And you don't have to keep checking, but if we put in, say, a negative number, I put in -1, I'm going to get a -1 times a positive number. And so even if we don't know what e is, but we do, it's about 2.7, you can automatically say, well, a negative times something that we know from experience is a positive number, is automatically a negative number, and that's automatically going to be smaller than this 1 over e. And the rest of these, it's just a matter of double checking with the calculator or whatnot to make sure that it's actually smaller. But like I said, I'm going a little bit overboard. All you had to do was put in this 1, see that 1 over e is larger than 0, so that means it has to be the absolute maximum because of the relationship that we talked about earlier. Okay, so this is one of those things where to check it, maybe it's better just type it into your graphing calculator, look at the graph and see if the highest point does occur at x is equal to 1. But if you really wanted to do it by hand, you can put in a handful of other numbers and just evaluate and check to make sure that it is smaller than 1 over e. Right, so that finally finishes up section 4.1. I hope that clarified some things. But again, let me know if you have any questions or concerns.